Okay, hi, I'm Jason, and I'm going to talk about the quantum advantage evaluation framework. Um, so first, to motivate this a bit, this is a quote from President Biden back in March, talking specifically about quantum computing in terms of owning the future as it relates to technology. Recently, we began a project with OUSD to develop an annually updated list of technical problems and research challenges which are likely to be addressable by quantum computers in the near term. I'll talk a little bit about what near term and long term means later in the slides. But basically, the objective of our research is to figure out when and where quantum advantage is to be found. And quantum advantage is simply solving some practical DoD problem faster or to higher quality of solution or both than any other alternatives, like, for example, classical state-of-the-art computing. So here we have some examples of DoD applications for quantum computing. On the left, there's combinatorial optimization and material science. And a big question is, over what time frame can we expect some type of quantum advantage for these applications? And there are sort of two distinct time frames. One might be the next 1 to 3 years, which will be called the NISQ era, or Noisy Intermediate Scale Quantum Computing era, which I'll describe more later. And the next is a longer time frame, say the next 10 to 20 years, as we develop larger quantum processors and implement quantum error correction. We know for sure there are applications that can demonstrate advantage in that time frame. But the bigger question is, what kind of advantage can we see in this shorter time frame? So to do this research, we developed the quantum advantage evaluation framework, which is pretty simple. It just takes whatever DoD relevant application we're interested in at the top, let's say combinatorial optimization, material science, or machine learning, and then it takes these applications on the left onto classical state-of-the-art computing. So what is the best classical devices and algorithms that we could use to execute these applications? And on the right, we have the quantum analog of the software stack. And this quantum full stack of software is still being developed, from the algorithms down through all the different representation levels. And the other thing is that we execute these applications and algorithms on real quantum devices, but we also utilize simulation of these devices on classical devices. And that's challenging because the whole point of leveraging quantum computing is to find quantum advantage or classically intractable advantage. So, but we need to use all these different methods so that we can perform the research. On the right is an example of the kind of output that we get from this framework. This is basically a benchmark plot, and in the orange and blue curves are projections of a quantum device and algorithm solving some DoD-relevant practical problem, and all the rest of the data points are classical state-of-the-art computing. So this is basically what the framework is about. It's about benchmarking, it's about implementation, it's about optimization. To go a little bit deeper into the quantum full stack, this is an example of one. This is mostly coming from IBM. We're an IBM Q network partner. So at the top, again, we have our application, whatever it is, and then we have to take that application and decompose it or rewrite it through these different levels of intermediate representation down to the actual quantum processors themselves. So at the bottom, we have some different quantum chips, again from IBM. You can see the progression in these chips in terms of size, connectivity, and so forth. On the right are some diagrams of what a quantum algorithm looks like at these different levels. So at the top is basically a quantum circuit at a higher level. In the middle is this quantum circuit that's been transformed according to the device constraints, whatever device it was being written to. And then at the bottom are the actual pulses that correspond to, at the physical device level, how do we actually implement these quantum gate operations. And so to get optimal performance, much like in classical computing, you've got to optimize across this full stack. Now, this full stack is also developing as we speak. It's not as well developed as classical computing, which has been developing for 60 plus years. And we have researchers working at all levels of the stack. And if you want performance, you have to be working at all levels of the stack and sort of co-optimizing or optimizing across it. OK, so to talk a little bit about where we are right now, this is a roadmap plot from IBM. Starting on the left in 2019, we had some 27-qubit devices. And where we are right now is basically here. This is a little bit old, but here we have a device that has 65 qubits. And these 65 qubits should be enough to do classically intractable calculations, except these devices are very noisy. So we're in this noisy intermediate scale quantum computing era. And this basically limits the circuit depths that we can execute and vastly limits the applications that we can demonstrate quantum advantage for. So as this roadmap progresses over to 2023, when they plan to have of 1,000 qubit chips, it's around this time that they're hoping to implement active quantum error correction, where the coherence times, the fidelity of the qubits and their operations can be extended much longer than they are now. And it's at that point that we know for sure there are applications that can demonstrate advantage. But a big question is, in this sort of intermediate time frame, what are the DoD relevant applications that can demonstrate advantage? Okay, another way of looking at the challenge of this scaling is to take a look at this progression of qubit of chip sizes, and then take a look at what's actually challenging in terms of scaling. Well, there are many challenges. One of them is simply cooling these devices. So IBM's technology requires that these chips be run at millikelvins in temperature. And this device in the photo is basically a dilution refrigerator, and the chip lives inside of it. And as the chips scale, cooling these chips is an ever-increasing challenge. You can see the progression in size of the dilution refrigerator on the left compared to the right, where it's 2 or 3x times the size. And so it'll be a big question whether or not they can scale this technology, cooling being just one of the challenges, as they attempt to achieve their roadmap to 1 million plus physical qubits beyond 2023. Okay, so IBM is not the only company building these devices. There are others who have different strategies, different technologies. So in the middle, you can see these different companies like PsiQuantum, IonQ, IBM, Google, et cetera. And they all have different roadmap projections, commercial roadmaps. And those are shown in the orange. And then there's a line fit through the orange, which projects out, if all of these companies and their projections come true, maybe this will be the pace of advancement that we'll see. In the blue are demonstrated experimental results from actual devices that have been built and tested and verified. And if you draw a blue line through these curves, you get quite a different projection in terms of advancement. And so the real question will be whether or not this projection from the commercial standpoint can be realized, or whether it will be more like the blue curve. The other thing to keep in mind is that these devices, in terms of number of interacting qubits, is not all you need for quantum computers and advantage. So for example, PsiQuantum has the most aggressive projection, where they are planning to have like of 1 million qubits by 2030, or around there. But they won't plan on using all those qubits as operational qubits. They're going to run quantum error correction with some overhead that will reduce the number of error-corrected logical qubits or operational qubits that you'll use on the device. So this reduction might take this 1 million physical qubits down to 100 or 1,000 logical qubits. So there's sort of a missing third axis on this plot in terms of qubit fidelity. But right now, we're mostly focused on this NISQ era, which I drew in a blue curve, or blue circle, this noisy intermediate scale quantum computing era. So as the companies continue building these devices and try to scale, what is the potential for quantum advantage even with these devices in this short time frame, let's say the next 1 to 3 years? Because in the fault-tolerant era, we know that there are applications that can show quantum advantage. But in this NISQ era, the question is even larger. Okay, so to summarize, our goal is to find quantum advantage for practical DoD problems that solve these problems faster or to higher quality or both than any other alternatives, for example, classical state-of-the-art. And the actions we have are to determine which applications have this chance, and then try to become quantum ready, that is, start integrating these devices into the workflows for those applications. And we also do have collaboration here at the SEI with CMU, where we're developing the Quantum Hub, where we have access to quantum software and simulation tools, and also real hardware. And it's a workspace for researchers to do this research. And if you have any interest, contact me for more info. And so this is the SDI team working on this, which has grown quite a bit over the past year. It used to be just a few of us, and now there's at least 8. And here are some of our SAMU collaborators, mostly Franz Franchetti in the ECE department, and students, researchers in both CS and physics department.